So let's do another example here of a similar replacement reaction. It's magnesium HCl. So when a strip of magnesium metal is placed in iron 3 chloride solution, the magnesium chloride solution results. So let's take a strip of magnesium metal and place that into iron 3 chloride. The formula for iron 3 chloride is FeCl3. And so when I look at this, this looks like the A plus BX pattern. If this is the A plus BX pattern, chlorides are soluble. Silver, lead, and mercury. If this is A plus BX pattern, we're going to form AX plus B. So AX would be magnesium with chloride, which is going to form MgCl2. And B, which will just be iron. Well, all right. Then I look. What do I look for chemical reactions? I look for precipitates, I look for stronger acid to weaker acid, and I look for things that decompose into gases like carbonic acid. But I have to remember that that this is not a metathesis reaction, this is a redox reaction. And so even though iron metal is insoluble, this precipitates. This doesn't precipitate because chlorides are soluble. So I get a precipitate of iron metal. In fact, that's what it said here. Solid iron also forms, which must be a precipitate of iron metal. Is that a driving force? No. The driving force for redox is not the same as driving force for metathesis and acid base. In fact, I can't use the driving. Just because precipitate forms doesn't mean anything. Just because a gas forms, does that mean it's going to drive the reaction? So if I take 2H2O liquid, and this is going to form 2 hydrogen gas plus 1 oxygen gas, here I form lots of gas. So is that going to drive the decomposition of water? No. Not at all. And so we have gas formers here. Gas formation works. Precipitation works for metathesis because the basic fundamental pattern of reaction doesn't change. But it doesn't work for redox because of this, because of the charges. You know, we get the Dr. Jekyll and Mr. Hyde type transformations in redox. So we don't have the Dr. Jekyll and Mr. Hyde type transformations, metathesis or acid base. And so what is the driving force? When we're looking for driving force, we compare the activities. And so let's look at the activity of A and compare it to the activity of B. So, the activity is just the strength of the reducing agent. Missed the recording for the first part. But for the first part, you can also check the morning class completely. And so we're comparing A and B. A is magnesium, which is here. B is iron. So which one's more active, magnesium or iron? Magnesium is more active. And so this is more active going to less active. And so if we're going from more active to less active, that's the driving force. So we expect this reaction to go. This reaction should occur. If the reaction goes, then what we can do is we can break this up into conventional, ionic, and net ionic. This would be the conventional or the complete equation. Let's go ahead and write the ionic equation for this. The ionic equation, we break up the strong electrolytes. So is magnesium metal a strong acid? No. Strong base? Soluble salt? No, it's not a salt. Salt would be an ion compound. This is just an element. And so magnesium salt just stays alone. There's no charge. Iron 3 chloride, is this a strong acid? No. Strong base? No. Soluble salt? Yes, this is a soluble salt. It's an ionic compound. And the soluble salts we dissociate, so we get iron 3 plus 3 chloride. Magnesium chloride, strong acid? No. Strong base? No. Soluble salt? Yes. So magnesium chloride dissociates into 1 magnesium 2 plus and 2 chlorides. We have to be very careful because a lot of mistakes are made here. A lot of mistakes are made, like people will forget the coefficient 3 and then have 1 iron and 1 chloride. That's not correct. We need 1 iron and 3 chlorides. A lot of people will forget to write the charge. Chlorine versus chloride, hugely different. Iron 3 versus iron metal, hugely different there too. So we can't forget the charge. Iron is not a strong acid, it's not a strong base, and it's not a salt. So that's just left alone. So are there any spectators here? Yeah, what's a spectator? Magnesium actually reacts. Because you see on the left, it's magnesium metal. On the right, it's a magnesium ion. Magnesium metal and magnesium ion are totally different. Just like sodium metal and sodium ion are totally different. That's the Dr. Jekyll and Mr. Hyde thing. And so on one side of this, we have Dr. Jekyll. On the other side, we have Mr. Hyde. How about the, well, there's no spectators because, I forgot to do something. I forgot to balance. You see it's not balanced? All of a sudden, 1 chlorine has disappeared. We can't have that. Atoms are neither created nor destroyed. And so before I got to this step, I should have balanced it. How can I balance this, though? It doesn't seem like I balance it so easily. Because I have 3 chlorines here, I got 2 chlorines here. I need to change it. Well, the easiest is to get the lowest common denominator, which is 6. So I'm going to put this to 2. So 2 times 3 is 6. And then I'm going to put this to 3. And so I get 3 times 2 is 6. So I get 6 chlorines here, 6 chlorines here, and that's balanced. But now the magnesiums are off. And so I'm going to put 3 magnesiums here, and the irons are still off. I'm going to put 2 irons here. So that's going to change things here. And so over here, I'm going to have 3 magnesiums. Now when I break this up, it doesn't break up into 1 iron and 3 chlorines. It's going to break up into 2 irons and 6 chlorine atoms. And then magnesium chloride here is not going to break up into 1 magnesium and 2 chlorides. It's going to break up into 3 magnesiums and 6 chlorides. And then the iron has got to be 2 irons here. Okay, now are there any spectators? Yeah. A spectator here would be chloride. And so the real reaction is going to be between magnesium and iron 2. And so we have 3 magnesium, solid, plus 2 iron, 3 plus. This is going to go to 3 magnesium, 2 plus, and 2 iron, solid. And so is magnesium here losing electrons or gaining electrons? In order to go from magnesium with a 0 to magnesium with a positive, did it lose electrons or did it gain electrons? Magnesium lost electrons. If something loses electrons, then we call it a reducer, we call it an oxidizer. Oxidizers take electrons. Reducers lose electrons. And so do you see what is magnesium? Magnesium's A. A is our reducing agent. And so magnesium is losing electrons. Well, who's taking the electrons then? The iron 3. The iron 3 is taking electrons because it goes from +3 to 0. In order to go from +3 to 0, it must have gained 3 electrons for each iron. We have 2 irons, so it gained a total of 6 electrons. And so iron 3 is what we call our oxidizer. And so do you see A is our reducer, B is our oxidizer, and what's our spectator? Our spectator is X, which is chloride. And so this is A plus BX. And so do you see how we can analyze the reaction here? And this is a single replacement reaction. And so what we say is that, magnesium is more active, this is less active. But there's another way we can do it. In general, all redox will have the same driving force. All redox have the same driving force. What we're doing is we're going from a stronger oxidizing agent to a weaker oxidizing agent, and a stronger reducing agent to a weaker reducing agent. And the way you visualize this is like this. Magnesium is our reducing agent. Iron 3 plus is our oxidizing agent. Now, over here, there are 2 ways of figuring this out. One is a conjugate relationship, but the other is just going backwards. If we were to go backwards and reverse this reaction, then iron goes from iron 0 to iron 3 plus. To go from iron 0 to iron 3 plus, it must lose or it must gain electrons. It must lose, so going backwards, iron is our reducing agent. That means magnesium must be our oxidizing agent. And so all chemical reactions are a battle between the forward and the reverse reaction. And so which one's going to win? Well, the dominant species are going to win. The stronger species win. And so which side is stronger? Well, we want this side to be stronger, so this side wins, so we get the forward reaction. However, this side is stronger, then we don't expect any reaction because it should go backwards. And so what we do is we consult the redox chart. When we consult the redox chart, which one's a stronger reducing agent, magnesium or iron? So here's magnesium, here's iron. The strongest is lithium. So magnesium is stronger than iron. And so what we're doing is we're going from a stronger reducing agent. A stronger reducing agent, we call that more active. To a weaker, iron's a weaker reducing agent. Weaker reducing agent is not going to be as reactive, so this is going to be less active. And so that's our driving force based on the activity series, going from a more active element to a less active element. In other words, going from a stronger reducer to a weaker reducer. Now the oxidizing agents follow the same. We only have to look at one. We only have to look at the activity of the reducing agents because the oxidizing agents will have the same activity based on the conjugate relationship. But we'll check it anyway. As far as oxidizing agents go, the top is fluorine. And so let's compare iron 3, there's iron 3 is up there. Iron 3 with magnesium 2 plus. So what's a stronger oxidizer? Iron 3 or magnesium 2 plus? Iron 3. So we're going from stronger to weaker. And so this is our driving force here. Or in terms of activity series, we're going from more active A to less active B. That's our driving force. Okay, let's stop here. We'll take a break and then continue after the break.